morning, and thank you for coming out this morning. Hopefully the topic of the keynote, or the name of the keynote, has you a little bit intrigued. So have you ever heard, just show of hands, have you ever heard anyone say, these kids don't know their facts? Only a couple hands, really? So what I want to do is I want to talk about what that means and what we're doing in our system in Halton. We've got an amazing staff, and they've been working really hard for the last 3 years on building your children's number sense. And I'll talk about how that interacts with knowing their facts. So these are the things I'm going to talk about today. There are 3 questions that hopefully you'll be able to answer by the time you leave here. So I want you to think about your youngest children. How many of you have children in kindergarten? Grade 1, grade 2, 3, 4, 5, 6, older? There's a lot of hands up. Holy mackerel, you've been putting your hands up a couple of times. So I want you to think about adding. And when your children are very, very young, they're starting to play with things. And they're starting to develop this concept called addition. So it takes up a lot of space in their brain. They're thinking about it. When they put things together, they get more. They might take 2 cars, and they might add 3 cars to it, and they put them together, and they get 5 cars. And think of your children when they were young, if they're older now. When they're doing that, they might do something called counting 3 times. So they might count 2 cars, they might count 3 cars, they put them together, and what do? They count them all again. And that tells us where they are developmentally in terms of the concept of addition. Now when I say to you, what's 2 plus 3, you know it's 5. That concept of putting things together and making more and really understanding what it means really takes up no space in your brain. It's a concept called called compression. So you know it so well. So when I move from cars, I might now then start to represent it with number. So I know that I don't need to always pull cars out of my pocket to be able to add 2 and 3. And now when I say 2 plus 3, I know it automatically. Takes up no space in your brain. You know that fact. But you understand what it means. None of us sat down our first day of school in kindergarten and were given a worksheet saying, what's 2 plus 3? We all had to understand what addition means, and then we can recall that fact. So when you think about mathematics, if everything is a series of steps and procedures, there's not enough space in your brain to hold it all in. So I want you to think about how many of you took math in high school? All of you. And you might have had something called a math exam at the end of the year. And you might have memorized something for that exam. Do you know it now? Right? You knew it for the moment, but there's not enough space, or you didn't conceptually understand it. And that's really what we're talking about. So what are the facts that kids need to know? How many of you believe kids need to know their facts? All of us. We all agree. But what are those facts? When we hear that, that's a big statement. The facts that kids need to know. What would be the facts that you want your kids to know? I hear somebody, I saw you mouth it, sir. Times tables? I heard you say times tables. So, times tables. Well, which ones? In our curriculum, we want our kids to really know up to multiply 12 times 12 and then 144 divided by 12. Does everyone agree with that? Those are your times tables, right? They're the things that you think about. And then there's also adding and subtracting. You need to be able to add and subtract to 20 and know that fact really well. Those are the facts your kids need to know. Every other fact, so if I give you a question like 734 plus 159, it's not a fact you need to know, but you need to be able to work with those numbers to add them together. because there's not enough space in the brain to think of, there's an infinite number of facts if we thought of it that way. So think about those facts. Here's our curriculum. In grade 3, students need to multiply up to 7 times 7, and then the division that goes with it. In grade 4, up to 9 times 9. And you'll see that in grade 1 and grade 2, they're building that addition, subtraction. Grade 3, same thing. And there's something that's bolded in each of those expectations in the curriculum, and it says using mental strategies. So I'm going to talk about what that means, because mental strategies are not recalling a fact. It's understanding numbers. This quote kind of highlights what I've just said. If every question in mathematics is something that we need to memorize, there's not enough space in our brain. So we all want our kids to be able to work with numbers, because numbers lead to algebraic thinking, and it also helps them conceptually understand and do some application. So I'm going to give you this question. This is a study that was done in the United States, and it was given to 7-year-olds. And teachers were asked to put their students into below average, average, and above average groupings. Now, I don't agree with that, but this is the purpose of the study. So all of the students did this question, and they got 21 as the answer. But how they got it was very different. So here's what the group in the below average did. So what are they doing? They're counting. Counting by? Counting by 1. Is it still going on behind me? Takes a long time to count by 1. It's very cognitively demanding for kids. So think of that with larger numbers. If children in grades 7 and 8 are counting by 1, that's going to take them a long time. So how do we as teachers not look at the answer, and this is what we really focus on. We know it's 21, but how did a student get 21? So we listen to students and say, well, if I'm counting by 1, where do I move them next? Let's look at the average group. And these are 7-year-olds. So this group did something called counting on. They knew 13, and then they added 1 by 1. So there's 2 different strategies as a teacher that I'm looking at in terms of a child getting the answer. Or they just knew the fact. They'd already consolidated that fact. Here's the above average group. Do you see 13 in orange? And do you see 8 in blue? So the thinking for students that are in the above average group, according to this study, they took 2 from 13. And those rectangles are called 10 frames. And what they allow students to do is to see 10 immediately. And we use them in our classrooms in early primary. We see 10 just as you would see 5 on a die. It's called subitizing. I see an organization. I'm not having to count them by 1. So really what kids are doing is they're able to pull numbers apart and put them back together. And that's true number sense. We want our kids to be flexible with numbers. So as a parent, as you're listening to your child, how are they counting? How are they working with numbers? You know those things where you add 1 here and subtract 1 and you're trying to memorize something? Why? So those are really important pieces as a parent. So you might be playing a game and you roll 2 dice. Watch how your child counts that. Are they counting every single dot on the die? Do they start with 4 and add 1, 2, 3? There's some pretty strategic pieces. Now, do not go home and tell your very young children that they can't count by ones. That is developmentally appropriate. But that's a good strategy to work with on your children when you're having fun. So now I want you to do this question in your head. I'm not going to pick anyone to answer. But I want you to think about how you're getting the answer of 80. Could someone share how they got 80? Yes. So the statement was, I add the 3 and the 4 to get 70, and I add the 2 and the 8 to get 10. As a teacher, I would say, 3? I don't see 3. I might see 30 and 40. Right? We talk about what those numbers mean and their place value, but I've been able to decompose those numbers and make them work for me. She's just used some flexibility in thinking. She's pulled those numbers apart. So we want our kids to, we're working on something called mental math, and this is one of the things that they should be doing in classrooms through number talks. So if you don't know what a number talk is, find a number talk session and go to it. Anyone have a different strategy? Yes? So she broke 32 into 30 and 2 and took the 2 and added it to 48. So now she had 30 and 50. Now it's really hard to follow what she's saying when you're just sitting there. So our teachers, their job is to represent the thinking in front of kids. This is I did not plant this. This was the strategy this lady used. She broke 32 and 48 apart and then worked with those numbers flexibly. That's one way. So think of yourself as a learner. You know, sometimes you're hearing everyone explain their thinking, and that's not the way you learn. Now I have a visual of what that looks like. This is another way, which is your way. So I'm thinking as a teacher, how am I going to represent that thinking? And I'm showing it. And you might have done something like this. So now what's happening in classrooms is our children are sitting there and they're listening. And they're saying, I got 80 using one way. You got 80 using another way. I'm going to compare my strategy with your strategy. I'm going to determine which one's better. That's pretty important. That's higher level thinking. It's not just doing a question, it's finding a better strategy that works for me. And so these are the strategies that we're talking about. So now I want you to think about the olden days. When you bring home a math worksheet or a math test and you get 5 out of 5, and it went on the fridge. And so that doesn't tell me anything about where you are developmentally in terms of your learning of understanding addition. So let's take the one in the middle. 4 plus 9 is 13. I don't know, did the child count by ones? Does the child understand that 9 plus 4 is the same as 4 plus 9? So how is your child answering some of those questions? Ask, listen. Did they count on from 9? You don't need to name the strategies, but listen to how they're pulling the numbers apart and making them work for them. So I was in a classroom the other day, and I had a teacher say to me, she said, I hear you're doing a talk. And I said, I'm going to be talking about kids don't know their facts. And she said, yeah, like sometimes I don't think kids know their facts. And I said, well, let's get a child and sit down and listen to them. So we pulled a student over, and of course she was good. She wanted to share what she knew. And I said, what's 2 times 5? And she said, 10. I said, okay. Well, what does 2 times 5 really mean? These are the things that this child shared with me. She took a ruler out, and she said, this is what 2 times 5 is. She told me it was 2 groups of 5, and she drew it. Does this child understand what 2 times 5 means? Absolutely. If I said, what's 2 times 5, a child told me 10, and couldn't show me any of these representations, I'd be very concerned. So we came down to the discussion around, what does it mean to know a fact? Do I understand it? Is the speed of recall that we're so concerned about as parents knowing a fact? So we came to talk about what are the facts that she knew and which ones didn't she know? And it was really which ones could she recall quickly and which ones couldn't she? And 7 times 8, guess what, was a tough one for her. So we worked on that. And she knew exactly what it meant. So then what's important? What's 7 times 8? What's 8 times 7? Get her to know that fact so that she can recall it. But really think about what it means to know your facts. All right, I'm going to make you do some more math. Anyone ever have a question come home for homework, and you are going to show your child how to do it, and they tell you, you don't know what you're doing? We don't do it that way. Math teacher, 17 years, running math in the board for a little bit. I have a daughter in grade 8. I know nothing. That's something that is probably going to be there. So how do we change what we do as parents? So this question, you probably get it home. Your child said, you're saying, I'm going to show you how to do this. I got it. Anyone do this? Anyone cross? Oh yeah, I can't take 7 from 0, so I'm going to borrow from my neighbor. Who's your neighbor? What does that mean? It means nothing. Borrow from your neighbor, your kids are looking at you like, I don't even think you talk to them. So that's a pretty big question, and I'm going to show you how to do it. It's called an algorithm. It's a strategy that you use to do it without models. And many of us use algorithms in life, and they're important. And our curriculum has algorithms in it. And we teach algorithms, but we don't start with that. How about thinking of, what does subtraction mean? It means the distance between 2 numbers. So I want to see in classrooms, when I'm walking into schools and seeing awesome stuff happening, I want to see a kid say, well, I know that 300 minus 287 means, what's the distance between 300 and 287? And I've got this number line thing in my head. I've got a mental picture of it. I'm going to jump to 300, and I'm going to jump to 105. Sorry, 300? Wrong question. I'm going to jump to 290, and then I'm going to jump to 300. I did it in my head. Don't you want your kids to be able to work with numbers in their heads? Anyone ever say, oh, these kids can't count change? Right, we hear that. That's another one. So how are the kids working with it? They have that picture in their head. And have any of you ever had, as students, a teacher say to you, that's great, you got the answer, but show your work. So you got to go back and show your work. Remember this thing? I'm going to go back and show you this. Why do I have to? I know that that model is showing my work. It's showing my thinking. And that thing called the number line goes all the way to calculus. It's a very valuable tool. So those are the things that your students or your children are working with. All right, homework. This is a copy of a worksheet. And if you can't read it, there are a couple of questions on here. It's 2 digits subtracting 2 digits. Grade 2. How many of these questions does your child need to do to show they know how to subtract 2 digits? How many? Have them make up a question for you. Make up a question for me and teach me how to do it. One question. Can they show you that they understand subtraction? Absolutely. Now then you get into the regrouping and everything. But that's the thing that, we're having parents say, I want to see lots of worksheets come home. I need lots and lots of homework. Well, what am I going to do with all those questions? Let's start to change the questions. You teach me. Here's a question, you teach me. Then find one that it doesn't work for. I'll give you an example. So it's really important that kids have models to represent what they know. So you might have seen these models come home in your child's work that they bring home. It might be a number line. It might be something called an array, which leads to algebra, which is really good. And I want you to think about this question. How do we read it? We might say 91 subtract 27, or 91 take away 27, or 91 less 27. Everyone agree with that? Doesn't matter. It means the same thing. So we talked a little bit earlier about what does subtraction mean? I have to have a conceptual understanding. It means the distance between two numbers. But we write it like this. We stack them. We got to stack them because there's a rule. This is how I do it. So this is the question, and this is how I'm asked to write it. So what happens with kids? She's so happy. What happens with kids? They start to do those rules that you're trying to teach them, right? Or that we try to teach them. And we try to take 7 from 1. But we can't. So what do? They try to take 1 from 7. Because they're not understanding what subtraction means. They're trying to memorize these rules. And then comes the neighbor again. So what's a faster way of doing this question? This is what subtraction means. This question, 91, subtract 27, means the distance between these two numbers. Okay, what I need you to do now is to put your hands in front of you. This is 91, and this is 27. Everyone good with that? So the distance between here is the answer to this question. And it's early Saturday morning, and those numbers aren't very pretty to work with. So what I'd like you to do is take your hands and move them 7 units to the right. Both hands. What's happened to the distance between your hands? It's the same. Put them back. Move your hands 20 units to the left. What's happened to the distance between them? Stays the same. So what we want to do, and this is a tool that we're using, it's called Dreambox. Many of you your kids are on Dreambox. The answer to this question is the distance between those two numbers, and they're ugly to work with. So where could I move those numbers, left or right, and how many to make easier numbers? Where would you move them? You could move 91 to 100, and you could move 27 to 36. And if you knew that that was 64 in your head, that would work for you. Is there an easier way for you? I heard someone say 3. 27 to 30 and 91 to 94. What's the answer? 64. It's the same answer. There's an infinite number of ways I could move those numbers, but isn't that a lot easier to understand conceptually what it means than stack them? I should start to have mental pictures of those numbers in my head and be able to work with them. That is mental math. That is mental math. It's pretty neat. So I talked a little bit earlier about the importance of algorithms. And yes, this is what we're leading to, but how do we do it? So we start with that model and an understanding. If I add the same number to each, it doesn't change the distance between them, right? So if I add 10 to 91 and 10 to 37, I'm adding 10 to 91 and 10 to 37. I never have to borrow again. I never have to borrow again. I get 64. Somebody tricked you in your schooling, didn't they? They made you borrow from your neighbor. So remember this question. If I take the same number away from each, so if I move it to the left, the distance stays the same. Don't need to borrow. The distance between those two values are the same. Are the numbers different? Yes. Is the distance between them the same? Yes. So these are some of the resources that you might want to look at. On the left, it's a site called mathies.ca, and it's created by the province of Ontario. There is a parent section. This is going to be shared, and Ruth will explain how it's shared. There's also, in the middle, ucube.org. Jo Bowler is a professor at Stanford University, and she's put together some fabulous tips for parents on supporting your children and helping them feel successful in mathematics. And then on the right, we have a couple of videos that are on our board website, a longer version of this sort of talk that I talked about this morning. And there's also a webcast on Dreambox. So if your children are learning using Dreambox and you want to look at it a little bit more, there's a longer presentation.